Welcome! In this session, we'll explore an intriguing problem from LeetCode, number 1105, filling bookcase shelves. This problem challenges us to optimize the arrangement of books on shelves while adhering to certain constraints. We'll break down the problem, examine potential solutions, and analyze their complexities. Let's dive in and get started. In this problem, you're tasked with organizing books onto bookshelves in a way that minimizes the total height of the shelves. Each book is represented by a pair of numbers, its thickness and its height. The goal is to place these books in the given order onto shelves, where each shelf has a maximum allowable width. Books can only be placed together on the same shelf if their combined thickness doesn't exceed the shelf's width. Additionally, you can start a new shelf at any point, but you cannot change the order of the books. The output will be the minimum total height of the bookshelves after optimally arranging the books. Let's consider an example to understand this better. Suppose the input is a list of books represented as 1, 1, 2, 3, 2, 3, 1, 1, and the shelf width is 4. The first book, with a thickness of 1 and a height of 1, is placed on the first shelf. Next, the second and third books, each with a thickness of 2 and a height of 3, are placed on a second shelf, since their combined thickness is 4, which fits within the shelf width. Finally, the fourth book, with a thickness of 1 and a height of 1, is placed on a new shelf. This arrangement results in a total height of 4. Breaking it down, the total height is calculated by summing the heights of all the shelves. The first shelf has a height of 1, the second shelf has a height of 3, and the third shelf has a height of 1. Adding these together gives a total height of 1 plus 3 plus 1, which equals 4. This is the minimum possible height for this arrangement of books given the constraints. Now, let's look at another example. Here, the input is 1, 3, 2, 4, 3, 2, and the shelf width is 6. In this case, all three books can fit on the same shelf because their combined thickness is exactly 6, which matches the shelf width. The height of this shelf is determined by the tallest book on it, which is 4. Since all the books fit on one shelf, the total height is simply 4. This demonstrates how placing books optimally on a single shelf can sometimes minimize the total height. Finally, let's review the constraints and edge cases. The total number of books will be between 1 and 1,000. Each book's thickness will be at least 1 and at most equal to the shelf width, which can go up to 10,000. Book heights will range from 1 to 1,000. For edge cases, if there's only one book, the total height will simply be the height of that book. If all books have the same dimensions, the shelf width determines how they're grouped. When the shelf width is very large, all books can fit on a single shelf, minimizing height. Conversely, if the shelf width is very small, each book must be placed on its own shelf, resulting in a total height equal to the sum of all book heights. To solve this problem, one of the approaches we might initially consider is the brute force method. The intuition behind this approach is straightforward. For each book, we decide whether to place it on the current shelf or start a new shelf. When adding a book to the current shelf, the total thickness of that shelf increases, but its height remains the maximum height of all books on that shelf. On the other hand, starting a new shelf resets the width constraint for any subsequent books but adds the height of the new shelf to the total height. To implement this idea, we use recursion with backtracking to explore all possible configurations of book arrangements, calculating the total height for each configuration and returning the minimum height. However, this approach has significant trade-offs. While it's simple to implement conceptually, its time complexity is exponential because we're exploring all combinations of book placements. For larger inputs, such as when the number of books is 1,000, this method becomes computationally infeasible, and we need a more efficient solution. A more optimized approach to this problem is using dynamic programming. The key idea here is to avoid trying all combinations by storing results of overlapping subproblems and making optimal decisions at each step. We observe that the books can be processed sequentially, and the decision to place a book on the current shelf or a new shelf depends only on the books that come before it. To formalize this, let dp I represent the minimum height needed to place the first I books. To compute dp I, we iterate backward through the previous books to determine the optimal way to split the books into shelves. As we iterate, we dynamically update the shelf height and width to ensure that the current book fits. The implementation begins by initializing dp 0 as 0, which represents the base case where no books result in zero height. Then, for each book, we iterate backward to calculate the minimum total height and store it in dp, I. At the end, dp, n, gives us the result. This method improves efficiency significantly, with a time complexity of O, n squared, due to the nested loops and a space complexity of O, n, for the dp array. The dynamic programming approach offers a much more efficient solution compared to brute force, especially for larger inputs. However, it does come with its own considerations. While it avoids the exponential growth in computations, careful implementation is required to handle edge cases, such as books that barely fit within the width constraints. Ultimately, we chose the dynamic programming strategy due to its balance of performance and simplicity. Although the brute force method is conceptually valid, its exponential time complexity makes it impractical for larger datasets. The DP approach, on the other hand, efficiently handles the constraints by leveraging the sequential nature of the problem and the overlapping subproblems. This approach is efficient with O, n squared, time complexity, scalable for real-world scenarios, and elegant in its ability to avoid redundant computations with the derived recurrence relation. These advantages make it the ideal choice for solving this problem. When comparing the two approaches, the differences in efficiency become clear. The brute force method, while simple, has high computational complexity and is not feasible for large inputs. In contrast, the dynamic programming approach is optimal within the given constraints, with manageable time and space requirements. The turning point in solving this problem was recognizing that it could be broken into smaller subproblems. By dynamically splitting the books into shelves and using results from overlapping subproblems, we were able to minimize the total height. This insight allowed us to move from a brute force solution to a more efficient and scalable dynamic programming approach, highlighting the power of leveraging problem structure to optimize computation. In this problem, we are tasked with placing a given set of books on shelves in such a way that the total height of all shelves is minimized. Each book has a fixed width and height, and the width of books on a single shelf cannot exceed a specified limit called shelf_width. Additionally, the height of a shelf is determined by the tallest book on that shelf. To solve this, we use dynamic programming. We define dp, I, as the minimum total height required to arrange the first I books optimally. The ultimate goal is to compute dp, n, where n is the total number of books. To break this problem down further, we identify that for each book I, we have two options. We can either place the book on the same shelf as previous books or start a new shelf with this book. The transition relation for the dynamic programming approach is expressed as dp, I, equals min, dp, j1, plus max_height, j, I, where we iterate through all j such that books from j to I can fit on the same shelf. This allows us to explore all valid configurations for placing the books efficiently. Here, the term max_height, j, I, represents the height of the tallest book among books placed between indices j and I. Meanwhile, dp, j1, gives the optimal solution for all books before index j. To start, we initialize the base case. If there are no books, then the total height is 0, so dp, 0, equals 0. Next, we iterate through all the books. For each book I, we initialize two variables, current_width to keep track of the total width of the books on the current shelf and current_height to track the maximum height among those books. Then, we iterate backwards from book I to j, updating current_width by adding the width of books, j, and adjusting current_height to be the maximum height among books from j to I. If at any point current_width exceeds shelf_width, we stop considering more books for the current shelf. Otherwise, we update dp, I, as the minimum of its current value and the total height calculated as dp, j1, plus current_height. This iterative process ensures that we explore all valid configurations to minimize the height. Finally, the result is stored in dp, n, which represents the minimum height required to arrange all the books. There are a few key insights to keep in mind for this problem. First, greedy approaches, such as placing books based solely on their height or width, do not guarantee optimal solutions. This is why dynamic programming is necessary to evaluate all possible arrangements. Second, to improve efficiency, we can prune unnecessary calculations. For example, if the cumulative width of the current shelf exceeds shelf_width, there's no point in considering additional books for that shelf. Another optimization involves pre-computing the height of books for each potential range. Instead of recalculating the maximum height between indices j and I repeatedly, we can iterate backwards and maintain the maximum height seen so far. Moving on to the data structures, we use a dynamic programming array dp of size n+1 to store the minimum height for the first I books. This allows for constant time access to previous solutions. During the nested iteration, we also use variables like current_width and current_height to dynamically calculate valid configurations. For complexity analysis, the outer loop runs for n books, while the inner loop, in the worst case, also runs up to n times. This gives us a time complexity of O, n squared. The space complexity is O, n, due to the dp array. Finally, we must consider edge cases, such as scenarios where there is only one book. In such cases, the solution must handle placing the book correctly on a single shelf. Other edge cases include situations where all the books fit on a single shelf. Here, the algorithm must correctly compute the minimum height as the height of the tallest book. Conversely, if some books are wider than shelf_width, the algorithm should either return an error or handle the situation gracefully, depending on the problem's requirements. Additionally, when books have drastically varying heights, the algorithm must still arrange them in a way that minimizes the total height of the shelves while adhering to the width constraint. To illustrate how the algorithm works, consider a specific example. Suppose we have 3 books with dimensions, width equal 1, height equal 3, width equal 2, height equal 4, and width equal 3, height equal 2, and the shelf_width is 4. Initially, dp, 0, is set to 0. For the first book, it fits on the first shelf, so dp, 1, equals 3, which is the height of the first book. For the second book, we have 2 options. If placed on a new shelf, the total height becomes dp, 2, equals dp, 1, plus 4 equals 7. However, if placed on the same shelf as the first book, the current width becomes 3, and the current height is updated to 4. The total height in this case is dp, 2, equals dp, 0, plus 4 equals 4, which is better. Thus, dp, 2, equals 4. For the third book, we again evaluate multiple configurations. If the book is placed on a new shelf, the total height becomes dp, 3, equals dp, 2, plus 2 equals 6. However, if we try placing it on the same shelf as the second book, the current width exceeds the limit of 4, so this arrangement is invalid. Similarly, placing the third book on the same shelf as both the first and second books results in a total width of 6, which also exceeds the limit. Therefore, the optimal solution is to place the third book on a new shelf, and the final result is dp, 3, equals 6. This demonstrates how the algorithm systematically explores all valid arrangements to minimize the total height while adhering to the width constraint. By leveraging dynamic programming and pruning unnecessary calculations, we achieve an efficient and robust solution for this problem. This implementation solves the LeetCode problem filling bookcase shelves using dynamic programming. The goal is to minimize the total height of shelves required to place all books without exceeding the maximum shelf width. We define a dynamic programming array dp, where dp, I, represents the minimum height needed to place the first I books. The base case is dp, 0, equals 0, meaning no height is needed for 0 books. We then iterate over each book I from 1 to n. For each book, we calculate the minimum height considering all possible placements of books on the current shelf. We use a nested loop where the inner loop iterates backward from the current book I to determine how many books can fit on this shelf without exceeding the width limit shelf_width. Inside the inner loop, we maintain 2 variables, width to track the cumulative width of books on the current shelf, and height to track the maximum height of books on this shelf. If adding the next book exceeds the shelf's width, we break out of the loop. Otherwise, we update dp, I, to the minimum of its current value in dp, j1, plus height, where j1 represents the books placed on previous shelves. After processing all books, dp(en) contains the minimum height required to place all books on the shelves. The solution efficiently considers all valid placements and ensures the optimal arrangement is achieved. The time complexity is O, n squared, due to the nested loops, and the space complexity is O, n, for the dp array. This is the Java implementation of LeetCode problem number 1105, filling bookcase shelves. The logic mirrors the Python implementation, utilizing a dynamic programming approach where the DP array stores the minimum height needed to arrange books up to a given index. Key Java-specific differences include the use of the arrays.fill method to initialize the DP array and the use of standard loops and array indexing. The overall time complexity remains the same, n squared, due to the nested loop structure. In this first example, we're working with 3 books and a shelf width of 4. Initially, we set up our dynamic programming array, dp, where dp, I, represents the minimum shelf height required to place the first I books. The array starts as 0, inf, with dp, 0, set to 0 because no books require 0 height. The total number of books, n, is 3. In the first outer loop, we consider placing just the first book. We initialize width and height to 0, representing the combined width and maximum height of books placed on the current row. In the inner loop, we process the first book by adding its width, which becomes 1, and updating the height to 1 as well. Using these values, we calculate dp, 1, as the minimum of its current value and the sum of dp, 0, plus the current row's height. This gives dp, 1, equals min, inf, 0 plus 1, equals 1. The updated DP array is 0, 1, inf at the end of this step. Next, we consider placing the first 2 books. Again, we initialize width and height to 0. In the inner loop, we start with the second book, adding its width, which is 2, and updating the height to 3. We calculate dp, 2, as the minimum of its current value and the sum of dp, 1, plus the row's height, resulting in dp, 2, equals min, inf, 1 plus 3, equals 4. Then, we consider placing the first and second books together. Adding the width of the first book brings the total width to 3, which is still within the shelf width. The height for this row becomes the maximum of the 2 books' heights, which is 3. Using this, we update dp, 2, again as dp, 2, equals min, 4, dp, 0, plus 3, equals 3. The dp array now becomes 0, 1, 3, inf. Now we consider placing all 3 books. We begin with width and height set to 0. Starting with the third book, we add its width, updating width to 2, and set the height to 3. Using these values, dp, 3, is updated to min, dp, 3, dp, 2, plus height, equals min, inf, 3 plus 3, equals 6. Next, we include the second book along with the third. Adding the width of the second book results in a total width of 4, which fits within the shelf width. The height remains the maximum of the 2 books' heights, which is 3. We then update dp, 3, as dp, 3, equals min, 6, dp, 1, plus 3, equals 4. Finally, we attempt to add the first book as well, but the total width exceeds the shelf width, so the loop breaks. The final dp array is 0, 1, 3, 4, and the minimum shelf height required is dp, 3, equals 4. In this second example, we examine an edge case where there is only one book with dimensions 2, 4, and a shelf width of 4. We initialize dp as 0, inf, where dp, 0, is 0, and n is 1 since there's only one book. In the outer loop, we consider placing the first book. Starting with width and height as 0, we process the single book in the inner loop. Adding its width results in a total width of 2, and its height becomes 4. We then update dp, 1, as dp, 1, equals min, dp, 1, dp, 0, plus height, equals min, inf, 0 plus 4, equals 4. At the end of this step, the dp array is 0, 4. With the dp array finalized as 0, 4, the minimum height required to place the single book is dp, 1, equals 4. Next, we move to another example where the shelf is wider, and we have 3 books with dimensions 1, 2, 1, 3, and 1, 4, while the shelf width is 5. We initialize dp as 0, inf, with n equals 3. Considering the first book, we determine its width as 1 and its height as 2. Using these values, we update dp, 1, as dp, 1, equals min, dp, 1, dp, 0, plus height, equals min, inf, 0 plus 2, equals 2. The dp array becomes 0, 2, inf. When placing the first 2 books, we start with the second book, setting its width to 1 and its height to 3. This gives dp, 2, equals min, dp, 2, dp, 1, plus height, equals min, inf, 2 plus 3 equals 5. Next, we consider placing the first and second books together. The total width is 2, and the height is the maximum of the two, which is 3. We update dp 2 again as dp 2 equals min 5, dp 0 plus 3 equals 3. For all three books, we begin with the third book, setting its width to 1 and height to 4. This updates dp 3 to dp 3 equals min dp 3 dp 2 plus height equals min inf 3 plus 4 equals 7. Then, we consider the second and third books together, with a total width of 2 and height of 4. This updates dp 3 to dp 3 equals min 7 dp 1 plus 4 equals 6. Finally, we evaluate placing all three books together. The total width becomes 3, and the height is the maximum of the three books, which is 4. Using these values, we update dp 3 as dp 3 equals min 6 dp 0 plus 4 equals 4. The final dp array is 0, 2, 3, 4, which means the minimum shelf height required to arrange all three books is dp 3 equals 4. The time complexity of our solution can be analyzed by looking at the nested loops driving the dynamic programming approach. First, the outer loop iterates through all the books, from the first to the nth book, so it runs n times. Inside this loop, we have an inner loop that iterates backward from the current book index I to j, stopping either at the beginning of the list or when the shelf width constraint is violated. In the worst-case scenario, the inner loop runs I times for each iteration of the outer loop. This means that the total number of iterations across both loops is the sum of integers from 1 to n, which gives us n times n plus 1 divided by 2. Simplifying this, we find the dominant term is n squared, so the overall time complexity is O, n squared. Within the inner loop, each iteration involves several constant time operations. These include adding the width of the current book to track the total shelf width, updating the maximum height of books on the shelf, and calculating the dynamic programming value for the current subproblem, dp I. Each of these actions takes O1 time. Since the inner loop runs up to I times for each outer loop iteration, the total operations within the inner loop sum to O(i). Combining this with the outer loop's n iterations, the dominant work still comes from the nested nature of the loops, resulting in an overall time complexity of O(n squared). For space complexity, the dynamic programming solution primarily uses the dp array to store the minimum height needed for each subproblem. The size of this array is proportional to the number of books, n, requiring O(n) space. Additionally, we use a few temporary variables, such as width and height, to store intermediate values during computation. These variables don't depend on the size of the input and therefore use constant O(1) space. Combining these components, the total space complexity of the solution is O(n), where the dp array dominates the overall space usage. When comparing this dynamic programming approach to a brute force solution, the improvements become clear. A naive approach would attempt to generate all possible groupings of books on shelves, which involves exploring all partitions. Since each book can either start a new shelf or be added to an existing one, the number of partitions is exponential, specifically O(2 to the power of n). For each partition, calculating the total shelf height would require O(n) operations, leading to an overall time complexity of O(n*2 to the power of n). In contrast, our dynamic programming solution optimizes the process by solving overlapping subproblems and storing intermediate results, reducing the time complexity to O(n squared). The space complexity is similarly reduced to O(n), making it far more efficient overall. Analyzing the best, average, and worst cases helps us understand how the solution behaves under different scenarios. In the best case, all books fit on a single shelf, and the inner loop terminates early due to the shelf width constraint. While the time complexity remains O(n squared), in big O terms, the constant factor is smaller. In the average case, books are distributed across multiple shelves, leading to varying numbers of inner loop iterations, but the overall time complexity is still O(n squared). In the worst case, each book starts on its own shelf, and the inner loop iterates fully for each book, ultimately reaching the worst-case complexity of O(n squared). Mathematically, the total iterations of the nested loops correspond to the sum of the first n integers, which simplifies to n times n plus 1 divided by 2. This confirms that the dominant term is n squared. For space, the DP array dominates with O(n) usage, confirming the overall space complexity remains O(n). When solving the filling bookcase shelves problem, there are several common mistakes to watch out for. First, not accounting for edge cases can lead to issues. For example, you might overlook scenarios where all the books fit on one shelf, or where the first book is too wide for the maximum shelf width. These situations can cause incorrect results or even runtime errors. To address this, always include checks for edge cases during development and testing. Another common pitfall in dynamic programming approaches is recomputing states unnecessarily. This happens when intermediate results are calculated multiple times, which increases the time complexity. You can solve this by using memoization or tabulation to store and reuse pre-computed results efficiently. Additionally, some beginners tend to overcomplicate the problem by using advanced data structures, such as trees or graphs, when simpler solutions with arrays or dynamic programming are sufficient. Breaking the problem into smaller subproblems and focusing on the constraints can help simplify your approach. Finally, misinterpreting the problem statement is a frequent source of errors. For example, constraints like keeping books in order or using shelves sequentially are sometimes misunderstood. Reading the problem description carefully and clarifying any ambiguities early is essential to avoid invalid solutions. Another important consideration is space complexity. Some solutions prioritize speed but use excessive memory, which can be problematic for larger inputs. Striking a balance between time and space efficiency is especially important in interview settings. Speaking of interviews, this problem often involves patterns seen in partitioning or knapsack problems, where identifying overlapping subproblems and optimal substructure is key. During an interview, it's also important to explain the trade-offs of different approaches. For example, you might discuss why a brute force solution isn't feasible for large inputs and how dynamic programming or greedy algorithms can improve efficiency. Clear communication is crucial. Be sure to walk through your thought process, from breaking the problem into subproblems to crafting the recurrence relation and addressing edge cases. Lastly, test your solution extensively with edge cases, such as when all books have the same dimensions or barely fit, to ensure robustness. This problem is also related to several other problems that share similar concepts. For instance, in LeetCode 1048, longest string chain, you work with sequences and dependencies, which is conceptually similar to arranging books in order. LeetCode 472, concatenated words, involves breaking down words into valid parts, echoing the idea of splitting books across shelves. LeetCode 887, superarray drop, and LeetCode 410, split array largest sum, involve partitioning and optimizing under constraints, just like this problem. Now, let's consider some alternative approaches. A brute force solution involves trying every possible arrangement of books, which ensures accuracy but has exponential time complexity. This approach is only viable for very small inputs due to its inefficiency. On the other hand, dynamic programming is much more elegant. By defining a DP table, where DP, I, represents the minimum height to arrange the first I books, you can efficiently decide whether to place a book on the current shelf or start a new one. While this approach requires careful handling of state transitions and edge cases, it's far more scalable and practical than brute force. Another approach is to use a greedy algorithm, where you place as many books as possible on the current shelf before moving to the next one. This method is efficient and straightforward, but it doesn't always guarantee an optimal solution. For problems that require precise optimization, such as minimizing the total height of the shelves, greedy strategies often fall short because they make decisions based only on immediate benefits without considering the broader implications. While faster, this trade-off in accuracy makes it less reliable for achieving the best possible result in every scenario. Understanding these trade-offs is key to selecting the right approach for different problem contexts. Thank you for joining me in solving problem number 1105, filling bookcase shelves. Today, we explored the problem's requirements, different solution approaches, and their complexities. Remember, dynamic programming and optimization techniques are crucial skills to develop for challenging coding problems. If you enjoyed this session, don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!